is called as Mantissa. Okay. Then these bits here, they represent what is called as let me just call it by the
भाई
name
एक
it
सेकंड
is. It's
रुक
called as
जा.
a biased exponent. I'll tell you what I mean by biased. It is called as biased exponent. And this bit here, this is nothing but your same bit. Okay, so this is the 32-bit format storage for any number.
हेलो.
If it was a 64-bit format, then what happens is that so this is like 1 bit here. These are like 8 bits here, and then you have 23 bits here. Right? So you just okay. So when it's a 64-bit format, then you have 1 bit to represent the sign bit. You have 11 bits to represent the biased exponent, and then I think 11, 12, so 52 bits to represent the Mantissa. So that's why I'm not writing the 64-bit format. Of course, you can obviously do it. Okay, so this is the standard format in which the numbers are stored. Okay, so now how exactly a computer would store a number? We'll take some examples. We'll take a small example first, and then we'll proceed with bigger ones, and then we'll also see. Okay. Right. So let me just explain this using an example. That's the best way to actually go about these problems that concern. Let me take a small number. Let me take a number like 13.5, and this needs to be represented in 32-bit format. Okay. So now I'll write some steps also. So that's like an algorithm. We can use it to solve these problems. So the first step is convert the decimal number into binary format. So if I make somebody a co-host in this meeting, they can also admit students, right? I'm not mistaken. Is it? Am I right? Is that accurate? Whatever I'm saying. Because a lot of people keep entering. So, Abhi, if I make you the co-host, can you take the responsibility of admitting students if they enter? I have actually made you. Yeah. Okay. Thank you. Okay. So the first step is you convert the decimal number into the binary format. Okay. So let's look at that. So you have 13. So 6 are 12. Remainder is 1. 2 3 are 6. Remainder is 0. 2 1s are 2. Remainder is 1. 2 0 times 0. So remainder is 1. Okay. We stop here. Uh, so we know that 13 is equivalent to 1101. Just a second. Hello. गुड मॉर्निंग. हाँ आप हाँ इंस्टॉल करना था वो आप मुझे 1 घंटे बाद कॉल करेंगे. मेरा क्लास चल रहा है तो मैं उसके बाद बात करूँगा. थोड़ा देर लेट हो जाएगी क्योंकि मैं अभी 11 बजे निकलूंगा घर से. तो मैं वहाँ पे अब से आप पहुँच जाइएगा. वहाँ पे हैं लोग जो इंस्टॉल करवा देंगे. आप पहुँच जाइए 11 बजे. ठीक. आप पहुँच जाइए फिर पहुँच के मुझे कॉल करिएगा. थैंक यू. sorry. So we're getting the MATLAB installed in the lab. We'll have 25 MATLAB licenses, basic MATLAB licenses. So you can write your codes and everything. Also, I think around 12th or maybe 13th of March, I am organizing a workshop, a one-day workshop on MATLAB for you people. It will be either Saturday or Sunday. It will be like a 3-hour program it's a workshop basically. So there you'll be able to learn the basics of MATLAB, and all those basics are also executable on Octave. So you don't really need to worry. Just learn these things so that you can straight away go to writing algorithms using MATLAB when the time comes. Okay. Anyways, so so moving ahead, this is 13, right? Then let's do something for 0.5. So that's also a simple straightforward procedure. You get 0.1, so you get a 1 here, and because you've got a 0 here, we don't even need to go further. So 0.5 is nothing but 0.1 in binary. Okay, so that means that 13.5 in decimal is nothing but 1101.1. So this was the first step, and we have obtained the binary equivalent of this. Okay. Then comes the second step. So in the second step is write the binary number into a standard scientific notation. Okay, so standard scientific notation is something of this type. So you'll have 1.x something, this entire thing, into 2 to the power of the exponent, which is e. So this is basically the Mantissa. Okay. So now the number that we have, so it's like multiplied by 2 to the power, and this is the exponent. Because it is binary, it is 2. If it was decimal, it would have been 10. If it was octal, it would have been 8, whatever. So now the number is 1101.1. So now we have to write it in this form. So this will be like this decimal should go here, then 1, 2, and 3. Right? So this can be written as 1.1011 times 2 to the power of 3. Right? You can write it like this. So this is your number now in the scientific notation. So this is the second step. The third step is that you need to find. So now we know the Mantissa. This is the Mantissa here. Okay, this is the Mantissa. So let me just denote this Mantissa by n. Okay. We know that the number is positive because it is 13.5. So we know what the sign bit is going to be. It's going to be 0. But now, if you remember, I had written something over here which is called as the biased exponent. Right? So biased exponent is the exponent is, so for numbers, the exponent could be positive, it could be negative, right? But if suppose you are to store a negative exponent, that means you would require another extra sign bit to tell whether the exponent is negative or not. Right? So that means that you would require 2 sign bits. One sign bit would be to tell whether the number itself is positive or negative. Then If the exponent is also negative, then you would require another sign bit to show that the exponent is also negative, right? So to get rid of that, what they did was that they said that, okay, let's make all the numbers from 0 to maximum. So what they did was they said that in IEEE format, what they do is that whatever is the exponent, they add 127 to it. Okay, so if you do that, then you obtain the biased exponent. So the third step is that obtain biased exponent by adding 127, okay, to exponent value. Exponent. Yeah. So that means I would call biased exponent as BE. So BE is nothing but 127 plus 3, which is 130. So this step is also complete. I'm just squaring all the important things that you need to do. Okay. Then the fourth step is, of course, since we're writing everything in formats of zeros and ones, you need to convert this biased exponent into its equivalent binary value. So then is convert BE from decimal to binary format. So can you quickly tell me what is the binary representation of 150? Anyone? 150 octal is what in binary? I'm waiting for an answer from you.
So can you hear me?
हाँ बताइए.
So 1, after that there will be 5 zeros and then 1 0.
1, 2, 3, 4, 5, and then 1 0. Okay. So yeah, so this is it, right? So this is it. Now we have all the things that we require. So now let's write the number in 32-bit format. So the first bit is 0 because it's a sign bit and it's a positive number. So this is 0. Then the next 8 bits represent the biased exponent. So here are the 8 bits for the biased exponent. So let me write it 1 0 0 0 0 0 1 0. So here are the 8 bits for the biased exponent. And then comes the mantissa. So if you look at it, the mantissa is 1011. So let me write it 1011, right? And then because there is nothing but obviously there are 23 bits attached to it, so that means all other bits are zeros. So you have 1 2 3 4 1 2 3 4 1 2 3 4. I'm writing it in fours first because it's easy to calculate. There's 16 bits. Then you have 1 2 3 4. Let me just do it. So 1 0 1 1, right? So you're going to think this only. So let me just write here 0 0 0, right? And ये जो bits हैं, this represents your matrix. So this is the 32-bit IEEE format for 13.5. Right? So this is what we update. Okay. So now let's look at how you would store the same number, but it's a negative number. So let's look at how the negative numbers are stored, and then we'll take some examples, and then we'll also take an example of if a format is given to you then how will you get the decimal number back? So that's also important, right? So let's look at another example. I think you can do this yourself also, but if I tell you how you actually go about it. So the thing is, you have minus 13.5. Okay, this is the number that you have, and you need to represent this in the 32-bit format. So there is just really two differences about storing a positive number and a negative number. The first thing is, of course, that the sign bit is going to become 1, right? So this thing here, this will make sign bit will become 1. That is the first thing. Okay. Then the second thing is, so this is the first difference. The second difference is that the Mantissa will now be stored in its 2's complement format. Will be stored in its 2's complement format. Yeah. So everything else is pretty much the same. So you have to repeat the 2 steps, but you have to remember these 2 things. These are very important. Okay, so just if you look at the number which is here, if you look at this number, then from this only we can come to this this problem. All the other 4 steps remain the same. So you will first write 13.5 in the binary format. You will convert it into a scientific notation format. It's also called as a normalized form in some books. So you will convert it. Then from there you will pick up the Mantissa. Then you will see what is the exponent value. You'll add 127 to it to obtain the biased exponent. Once you obtain the biased exponent, you will try to convert it. Not try to, you will convert it into its binary equivalent. And once you have that, then you are going to write them in the manner in which a negative number is to be written. So the first thing about a negative number is that the sign bit has to be 1. So the sign bit is 1. That's okay. Then the exponent and the bias exponent will be the same because the number is the same. So it doesn't really matter. It's the first derivative. So 0, 0, 0, 0, 0, 1, 0. So this comes into picture. But now the other 23 numbers are going to be basically the 1's complement of this number. So if you look at it, then let me just try to write it from here only. So this will become 0, 1, 0, 0. Then all these numbers are going to be 1. So you should probably calculate it. I think that will be better. So let's see. So I'm just writing the 1's complement here for the Mantissa. What is the number is written? Or maybe I should just write it down. So the number is 1011. That is 1011. 2, 3, 4. 4, 1, 2, 3, 4. 1, 2, 3, 4. Okay. It's 16. 16 and 4, 20, 23. One zero zero one 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 one. Then to this you add 1. So 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0, 0, 0, 1, 0, 1, 0. So this is what is going to come over here. So this 13.5 is going to be, so minus 13.5 is going to be 1, which is the sign bit. Then you have the exponents. So this is 1, that's 1, 0, 0, 0, 0, 0, 1, 0, exponent, and then you have 0, 1, 0, 1, char, and then you have 1, 2, 3, 1, 2, 3, 4, 4, 4. So this entire here gives you your negative number. So this is the 32-bit format representation for a negative number. Okay. Alright. So this is it. So now you know how to write this, but there is just one more case I want to consider. Sometimes what happens is that the fraction becomes repeating after a certain period of time. It's called as a recurring. Okay. So let's look at another example. I think I will ask you to give me answers to this so that we can see if you have developed some kind of an understanding for this process. So let's take another example. Let's keep it simple. Take a positive example only. So 263.3. Suppose this needs to be converted into a 32-bit format. Okay. So obviously the first step is you give me the binary representation of it. So start doing this problem and give me the binary representation of 263 first. What is 263? Binary representation. I'm waiting for an answer from you.
1, 5 zeros.
Yeah. 1, how many zeros?
5 zeros.
Okay.
After that, 111.
And you are?
So my name is Swastik.
Acha, thank you, Swastik. So this is it. So this is this seems about right. Yeah, that's right. Okay, so this is it. So this is 263, right? Then let's look at 0.3. What will be 0.3? What would be the binary equivalent for 0.3?
So 0 1 0 0 1 1 0 0
Mm-hmm.
1 1 and then
Yeah.
it's
So
recurring.
it's like recurring. It's like recurring,
Yes.
right? So let's look at this. Yeah, thank you. So this is 0.3. If you multiply it by 2, so you get 0.6. So it's like 0 linear. So this is 0, it comes in. Then you again multiply it by 2. So it becomes 1.2. So this 1 comes here, right? So then you pick 0.2 from here, you multiply it by 2. So you get 4.4. So you get a 0 here. Then you multiply it by 2, you get 8. You pick up the 0 again. And then you multiply it by 2, you get 1.6. You pick up a 1 here. Then you're left with 0.6. You multiply it by 2, you get 1.2. You get a 1 here. But then again you get 0.2. So you get this process repeating again. So basically you have 0, 1, and then you have 0, 0, 1, 1. Then again it will go to 0, 0, 1, 1, 0, 0, 1, 1. So it will continue. So one can say that this is 0, 1, 0, 0, 1, 1, 0, 0, 1, 1. decimal. Right? So this is that recurring example that I've taken. So because it's recurring, I think you can really clearly understand that here filling up 23 digits is not going to be too much of a problem, and then we'll have to stop at 23. So basically, one could say that there is some sort of a truncation error that will come into picture because you're going to stop at 32 bits while the number is going on. So this is also an example where there will be an error between the exact value and the value that your computer will be able to store, because it's a recurring number. You will have to just cut it short to 32, and you have to store Mantissa using only 23 bits. Okay, so so let me just write down this number now here. So this 263.3 decimal is equal to क्या था बताओगे जरा 1 5 zeros 1 2 3 4 5 उसके बाद क्या था
triple one.
अच्छा triple one. So this is it, and then you have 0 1
0 0 1.
0 0 1. So you have 0 0 1, then 1 0 0 1, then again 1 0 0 1, and you can just continue and see what happens. Okay, so this is the number. So you have obtained the first step. You have obtained the binary equivalent for this number. Now we need to write this number in the scientific form or the normalized form. So if you look at it, you take the decimal. We have to bring the decimal after 1. So this is 1 2 3 4 5 6 7 8. Right. So that means this number now becomes in the normalized form or in the scientific notation form. This number is 1.12345 111. किसी का माइक ऑन है, प्लीज बंद कर लीजिए. 0 1 0 0 1 1 0 0 1 1 0 0 1 1. कितने हो गए? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 and 8 0 हो गया 23 हो गया. ठीक है. And this is basically nothing but 2 to the power of 8. Something like this. So so this is the number in the scientific notation. Now this here, let me make it colorful. So this here is your Mantissa. So let me call it E. Okay. Now your exponent, this is your E. Okay. So then you calculate biased exponent. And biased exponent is 127 plus 8. And 127 plus 8 is 135. Okay. So this is your biased exponent. Now you write biased exponent in the
So 1 after that 4 zeros.
1 2 3 4, and then
So triple one.
1 1. Not triple ones coming. So this is it. So that's it. Problem is pretty much solved now. So now we need to write it. So we have the bias exponent also, we have the Mantissa also, and then we know that it's a positive number, so sign it is 0. So this is 0, number 1. Then you have 1 0 0 0 0 1 1 1. So this is done. And then you have the entire Mantissa. So that is 0 0 0 0 0 1 0 1 1 1 0 1 0 0 1 1 0 0 1 0 0 1 0. This is the answer. So that's it. So this is how you will store a recurring number. If this was something, if this was a negative number, then obviously this bit would have been 1 here, and this Mantissa would have been stored in its 2's complement. So then you know how to calculate that. So this is how a number is stored in the what do you call it? Repeated format. Okay. So now let's see. I think we have about 20 minutes left. So I think we'll just take one more issue. The issue is, If you're given a 32-bit format, how is it that you're going to come back to the decimal? Okay, so that's it. Let's look at that also. So now the problem is that given a 2-bit floating point, अच्छा एक चीज और I wanted to tell. Uh, 32-bit is also called as single precision floating point number, and a 64-bit is also called as a double precision floating number. So there are many books in which instead of writing floating point, they write single precision representation, double precision representation. So just remember, single precision means 32 bits, double would be 64. Given a 32-bit floating point real number, find its decimal. So how do we go about it? So now there are some steps I'll write it. Then we just go ahead. So first step is of course sign bit will tell whether the number, that's my son. Sign bit will tell whether the number is positive or negative. With positive or negative. Okay, so that's the first thing. All you need to do is just look at it. 0 means positive, 1 means negative. So if it is negative, then please remember that the mantissa is being stored in the 2's complement form. So you have to convert it again into the real form. So you have to again calculate its 2's complement, right? So just remember that. So I'll just write here that this is an important point, that if sign bit is negative, or if sign bit is 1, not write negative. If the sign bit is 1, the mantissa or I should write this. If sign bit is 1, evaluate 2's complement of the last 23 bits to get the mantissa. That makes sense, because if the sign bit is 1, the mantissa is not the mantissa, it's the 2's complement of the mantissa. So to get it back, you need to calculate its 2's complement. Okay. So this is the first thing. Biased exponent bits evaluate the decimal equivalent of the exponent. Okay. So how do you actually do that? So you will be given a bit pattern. So you will convert that bit pattern into a decimal number. So basically you will have something like this. You'll have x, 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 x. So you will convert this into some decimal number. This is for the bias exponent. Okay. Then what you'll do, the exponent is going to be basically biased exponent minus 127, because you added 127 to exponent to get bias exponent. So this is the this is how you will obtain the exponent, right? So this would be the exponent, and this exponent will be in the decimal form. So this would be basically in the decimal form, because your binary exponent has been calculated over here in the decimal form. So let me just write it here as P. So this is how you will obtain your binary exponent. Then the third thing is, you will then write it in the scientific notation as before. So that was basically 1 point, your x, 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 x. So this was your Mantissa basically, all multiplied by 2 to the power of exponent. Right. So these are bit patterns, right? So these are like the bit patterns of, let me just write, these are bit pattern of Mantissa. Okay. So now, once you obtain the bit pattern of Mantissa, you will apply the standard rule to calculate this into, to convert this into decimal number. So how do you do that? Let me, you know this, but let me just probably write it in a different place so that you can do it. Let me just say, so let me just call this pattern as X, Y, Z, W, E, Q, R, so on. So what would that be? So these are just bit patterns. X would be either 0 and 1, Y could be 0 or 1, Z could be 0 and 1, and times 2 to the power minus 1 plus Y times 2 to the power minus 2 plus Z times 2 to the power minus 3 plus W times 2 to the power minus 4 and so on. Okay. So this is how you will obtain the decimal format for the Mantissa. And then in the last step, you will obtain the decimal equivalent, and it has a standard formula. So the decimal equivalent is going to be minus 1 to the power of sign. So this S is the sign bit. It can be 0 or 1. So if it is 1, then you know that the number is negative. And then so then it is multiplied by 1 plus m. So m in the decimal format multiplied by 2 to the power of c, or 2 to the power of exponent basically. So this would be a decimal. That's it. Okay. So that's it. So let's take up a small example. And in about 10 minutes, I'll just quickly do an example so that you can know how to go ahead. So let me take a number. So this is, let's say this is 0, 1, 0, 0, 0, 0, 1, 1, 1. And then you have 1, 0, 1, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. This is the number. And you need to write its decimal. Okay. So this tells you that the number is positive. Good enough. Let's look at the exponent bits. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So if you look at it, so what is this? This is 2 to the power of 1 plus 2 to the power of 2 plus 3, 4, 5, 2 to the power of 7. So this is going to be equal to 134. Okay. So this is the value of your biased equivalent. Biased exponent, sorry. So you subtract minus 127 from it. So you will obtain 7. So this is your exponent. So you obtain the decimal of the exponent. Okay. Okay. So you need to write the decimal equivalent for this Mantissa. So we start from this 1. So this is 1 into 2 to the power of minus 1 plus 0 into 2 to the power of minus 2, which is this 0. Then 1 into 2 to the power of minus 3, which is this, plus 0 into 2 to the power of minus 4, which is this, plus 1 into 2 to the power of minus 5. Okay, and then you have all 0, so it will be all 0. So now can you tell me what is the answer for this? So this is 1 by 2 plus 1 by 8 plus 1 by 32. What is this? Can you tell me what will be the value? I just want someone to tell me this value. बताओ.
0.65625.
0.65625.
65625.
And you are?
25.
आपका क्या नाम है?
संजीत कुमार सर.
संजीत. Thank you. Okay, so this Mantissa का value आ गया है decimal format में. So now your decimal number is minus 1 to the power of sine, which is 0. Sine bit is 0. So is it 1 plus 0.65 265 into 2 to the power of 7. So whatever this is. So this is nothing but 1.65625. This is your decimal number. जो भी calculate होके आता है. Okay. So that's it. So this is how we represent numbers in 32-bit format. Positive numbers, negative numbers, recurring numbers, and then if there is any bit pattern given, you can convert back that bit pattern into the decimal format. In the next class, we'll look into the issue of error propagation, and we'll try to solve some numericals related to adding, subtracting, multiplying, dividing. How a computer would do that. We consider a hypothetical system with some number of bits. So we'll look into these problems and we'll solve some. What will be the error propagation and so on and so forth. So we'll look into that. I think this week we'll finish this unit. Yeah.
Sir, why minus 1 to power 0 and you put minus 1 to 0?
Oh, that just gives you positive or negative, right? So if this was a negative number, then minus 1 to the power of 1 would give a minus sign. So automatically a decimal number with a minus sign. Or you could just just not write it and just write a minus sign just by looking at the sign. So
But in conversion, sir, there was minus 1 to power 5. So what is the
I'm sorry?
Just,
Sir,
okay. Sir, in conversion, there is minus 1 to power 5.
minus 1 to the power of 5. ये
Yes, sir. Sir, in step 4.
in step 4
Yes, sir.
इसकी बात कर रहा हूँ, ये जो लिखा है.
Sir, in step 4, sir. Fourth step.
हाँ,
सर चौथे स्टेप में जो लिखा है माइनस 1 की पावर 5. यस सर.
ये 5 नहीं है, ये 5 नहीं है, S है, साइन बिट. इसको स्मॉल कर लो.
ओह अच्छा. ओके सर.
So let me just
Excuse me,
write it
sir.
here. S is sign bit. हाँ.
So for the biased exponent, like why we are using 127?
So I think to make it for most of the decimal numbers, I think if you look at it, so what is the minimum 8-bit that how many bits are there? 8 bits now. So you are moving from minus 128 to 127, right? So and 0 included in it. So if you add 127, so I think from minus 127 if a decimal, for example, there's an exponent which is minus 127, right? So if you add this bias exponent, if you add the number 127 to it, you will obtain the bias exponent as 0. So you can represent 0 as 0.00008 bits. If suppose you had let's say that you had a exponent as minus 3. Okay. So now to write this exponent using 8 bits or whatever number of bits, you would have also needed a negative how would you represent, how would the computer come to know that this is a -3 exponent but not a +3 exponent? You would have to use another sign bit to depict the minus of the exponent. Do you agree? जैसे कि हम लोग एक नंबर का नेगेटिव रिप्रेजेंट करने के लिए एक साइन बिट लगा देते हैं, उसी तरीके से एक्सपोनेंट नेगेटिव है तो उसके लिए भी मुझे चाहिए। तो उसको हटाने के लिए, एक एक्स्ट्रा बिट हटाने के लिए उन्होंने क्या किया, उन्होंने बोला कि हम इसमें एक ऐसा बायस ऐड कर देंगे ताकि IEEE took it to be 127। मेरे हिसाब से इसको 128 लेना चाहिए था, बट because it's a standard IEEE format and they use 127, so I've used that. But I hope that you now understand that for most of the numbers till negative power of -127, all of them will get converted into either 0 or positive exponents. So we don't need to have an extra sign bit for representing the exponent numbers, except for when you write the smallest number, which is -128 exponent. There is a problem in this system right now. I hope I have answered your question.
Yes, sir. Thank you, sir.
Okay. All right then. I'll see you tomorrow. Tomorrow is a 9 o'clock class, right? So we'll have that online as well, so you can eat and do it. I had a talk with the so faculty meeting was on Friday, and we had a discussion on this thing. So they said that a lot of faculty members had issues because the classes would then extend to 6 to 7, so they were not really interested. But then I thought the best thing to do is just keep the morning classes in the online, or whichever class you say will be in online mode, we'll do it in online mode. But I think after maybe another week or two, when we start writing codes, I would want at least one class at 10 o'clock in the class, so that we can all sit together and write these codes. I would also encourage you people to go after college hours or on Saturdays and Sundays to this lab in which I'm installing MATLAB today. Actually, we got the license 2 years back, but because of COVID, we could not get it installed, all of them. And we also had some LAN issues that has been corrected. So now, I think by today, we'll have licensed version of MATLAB, 25 licenses in the computer lab. So maybe a week from now after Holi, 2 weeks from now after Holi, once you've done that workshop as well, you guys will start writing codes. So I would encourage that you do that in the lab. And I would want one class. We'll see which class that is. It'll definitely not be the 9 o'clock class, but it will be definitely a 10 o'clock class where we'll be meeting offline and we'll sit together and chat and write some codes. Okay. Another thing I wanted to talk about is that I found out that Damodar is not giving breakfast, and you have to go to Kaveri. So I asked my office to formally write a request that we should start the breakfast service in Damodar as well. A very informal reply came saying that the number of students are not very high there right now, but I don't really agree. तुम लोग ही मिला के 100 तो तुम ही लोग हो गए हो. So I don't know why they said that, but I would ask. But regardless of that, we'll keep the 9 o'clock class on so that we can eat. Sometimes you can eat. So that's not the objective, but we can't really shift the timetable far below, because faculty members not only from school but outside school are also having issues with it. And the general standard time is 9 to 6, so that's why. Okay, I'll see you tomorrow.
Thank you, sir.
Good day.
Bye, sir.
Bye, sir.
Thank you.
Bye, sir.
Thank you. Bye, sir.